All right, we're going to work through a quantitative problem on entropy change during a phase change. So I'm going to just start by reading our question. The normal freezing point of ethanol is negative 114 degrees Celsius, and its enthalpy of fusion, which I have a little star to define it down here, is 100 joules per gram. In the following questions, consider the system to be 2.0 grams of frozen ethanol with a temperature of negative 114 degrees Celsius. So before I even get into any of the questions here, I'm going to just draw out like what I have. I think for me, a visual is very useful. So I have a cube, 2.0 grams of ethanol, and it's solid. And it is already at the melting temperature, but just like slightly um, underneath it. Okay. Okay, so it's right there. In other words, if we were looking at a phase change diagram for ethanol, we would be right here. Okay, so here's where we have our solid. We're heating it up, and then we hit our phase change, our melting point, right? And so all of the energy added, all of the heat added is used to break up the interactions between the ethanol molecules in that solid phase and to get it into the liquid phase. And then this curve, this is the liquid. We're heating that up. Here is boiling. And again, we're not increasing the temperature of the system. We are just pulling out those particles into the gas phase. And then here we're heating up the gas. Okay, so we're right. The question has us right here. Okay. And we are thinking, since it's already frozen, we're going to be asking about it melting. So we're going to a puddle of ethanol that would also be at negative 114 degrees Celsius. And this will be a liquid. Okay, really, really cold liquid. And again, I like to do this before I get into any of the questions because I already know a lot about this system, right? I can tell you the sign of enthalpy, of the enthalpy change, and the sign of the entropy change. And so I can ground myself before I get into the questions and see the distractors, which might pull me off course. So I would look at this and say, I know that delta H for the system. So for this process is going to be endothermic. So it's positive. It's going to be a positive value because we need to put in energy. So energy is required to make this happen, right? If I was going the other direction, if I had ethanol that was already in its liquid form and I was freezing it, that is exothermic and would be a negative sign. So from the system's perspective, the system needs to absorb some energy from the surroundings to make this happen. And as this happens, we are increasing the entropy of our system. Okay, I know that because I have a lot more microstates when I provide that translational freedom to my ethanol particles in the liquid. Here they're locked into place. You can think about it, they're in some like crystal structure where it's like they're all perfectly aligned and they can't move. They can vibrate, but they can't rotate and they can't translate. As soon as they get here, now they can move around, right? And so that means a lot more positional freedom, which means many more configurations, which means an increase in entropy. Okay, so we can tie all of these concepts together even before we get to answering this question. Okay, so what is the entropy change of the system, delta S, when the ethanol melts? Okay, so we're going to use in this case, we don't have any quantitative information. Like we don't have standard molar entropies for ethanol. And so I have to use the information that was given to me. I have the enthalpy of fusion. So I'm going to say that that energy was absorbed by my ethanol at negative 114 degrees Celsius. So I'll use this equation. So delta S of the system absorbed, let's see, 200 joules because I have 2 grams. Each gram required 100 joules. And this happened at negative 114 degrees Celsius. I'll add 273 to get myself into Kelvin. So 200 divided by 114 plus 273. Just doing this on my calculator right now. So that is 1.26 joules per Kelvin. Okay. And so that makes sense, right? That's positive. We predicted that it would be positive. The system is increasing in entropy. Next question, what is the entropy change of the surroundings? Okay, when the ethanol melts at negative, so just ever so slightly, infinitesimally slightly higher in temperature, right? We've added 1 over infinity so that we are trying here, you should read this as I'm trying to emulate a reversible process. We're trying to achieve a reversible process. Okay. So I'm going to get essentially equal and opposite. The surroundings lost the heat that was needed to melt that ice or that ethanol solid, right? And so from its perspective, from the surroundings perspective, it's equal and opposite in size. So I'm going to have 2.0 grams times negative 100 joules per gram. And it happened at essentially the same temperature, which was 159 Kelvin. Okay, so this would give me negative 1.26 joules per Kelvin. Okay, and again, I would look at and see, oh, if I added these together, delta S of the universe would be, delta S of the universe would be 0, which is characteristic of a reversible process. Okay. So I have 1.26 joules per Kelvin here and negative 1.26 joules per Kelvin here. And then lastly, what is the change of the universe when the ethanol melts at negative 30 degrees Celsius? So I've now changed the surroundings. Okay, the surroundings are now at a higher temperature, but my ethanol is still in its solid form, which means it is still at negative 114 degrees Celsius. I've just picked it up and plopped it down into a warmer room. Okay, so this number is still the same. Our delta S of the system hasn't changed, but delta S of the surroundings has changed for this process. Now it's still giving that heat, it's still providing the heat, but it means less, right? It's like it's at a warmer temperature, and so it has more energy to give at that warmer temperature because we can associate temperature with kinetic energy. So it like already has more energy at this higher temperature. So giving some energy away is not as significant when it's at this higher temperature. And so that means this is going to be a spontaneous process because we're going to find that delta S of the universe is greater than 0. So do same top calculation. But now we don't have 159 Kelvin, we have 243 Kelvin. So 2 times negative 200 divided by 243. Okay, so that's negative 0.82 joules per Kelvin. So now I get to calculate delta S of the universe as the sum of these two terms. And that's from the first question, 1.26 plus a negative 0.82. 0.44 joules per Kelvin. So that is positive. We just found that delta S of the universe is greater than 0. Therefore, the ethanol solid that we had, our 2 grams of solid ethanol will spontaneously melt. at negative 30 degrees Celsius.